Okay, folks. Today what we're going to talk about is what's called a matched pair, or what's called a mean difference. So I'm going to do a quick review of kind of the stuff we've talked about already. So first one we talked about is called the one sample t interval. It's where we have literally one sample. And what we have is we have our x bar plus or minus t star, sx over square root of n. Basically, it's saying this is how I figure out my interval for if I'm trying to estimate the answer to like one sample, like the real answer based on one sample. Okay, what we talked about last class is a two sample. And the way you'll see this is you'll often see it written as difference in means. And notice that's a plural, means, two means. And what we do is we take the difference of our two different sample means, we add and subtract t star again, but now what we do is we combine the standard deviations. And just so you know, all of this is on your formula sheet, so you don't really need to remember it explicitly. Our confidence intervals right down here, statistic plus or minus critical value, standard error statistic. And when you flip to the back, when we have two populations, it's x bar 1 minus x bar 2, and then there's our standard deviation right there. So that's right, it's on our formula sheet. We just need to know where to find pieces. And then we have 2 degrees of freedom, n minus 1 and 2 minus 1. So with a one sample, it's just the 1 and minus 1. And with a two sample, there's two minus 1s. And we take the smaller of the two. It's called our conservative degree of freedom. It errs on the side of making our interval a little bit bigger. But we're also going to go through and we're going to write down the number from the calculator. So today, what we're going to see is, so again, notice it's a difference in means. Today, what we're going to talk about is we're going to talk about mean difference. Mean difference. So the biggest thing you notice is singular. So what this is it's an instance where I'm going to be given two samples, but I'm going to run my interval on the difference of the two samples. So taking a look at this question, teenagers spend on average approximately 5 hours online every day. Do parents realize how many hours their children are spending online? A family psychologist conducted a study to find out. A random sample of 10 teenagers were selected. Each teenager was given a Chromebook and free internet for 6 months. During this time, their internet usage was measured in hours per day. At the end of the 6 months, parents of each teenager were asked how many hours per day they think their child spent online during this time frame. So what ended up happening is, first line, this is our first sample. So this is our sample 1. So this is our sample 1, and this is the actual hours that teenagers spend online. This is sample 2. Okay, so now notice, we actually do have two samples, but they have a pair to it. So what you're going to see is oftentimes this thing is referred to as a matched pair. What it means is our samples have a way to link together. So what we're going to do on this is we have the two samples. This is how many hours they really spent online per day. This is the perceived hours online per day that the parents had. So what we're going to look at is we aren't going to be real keen on, so what I did is I put the hours that teens actually spent online in L1, their parents' perception in L2. What we really care about is the difference. We really care about what is the difference between the two. And that's what we're going to run the test on. So what's going to happen is we're going to go through and we're going to do this two samples, but we're going to treat it as the one sample difference. And that's how we're going to approach the problem. Okay, going back to it. So what I was saying is what we need to do is we need to not treat it as two different samples. We need to treat it as the sample of the difference. So really what I care about is I care about that L3 column. So the first question says, make a dot plot of the difference, because this is what we really care about. So again, let me show you how we use our calculator to do that. You could make a dot plot if you want. You could just go ahead and draw a number line and go ahead and put those dots on the number line. But I want to show you that your calculator's got it. Since I need to use my calculator to do the analysis anyway, let's use our calculator to do the dot plot. So what I had said was histograms are really good at showing skew. So what I'm going to do is I'm going to pick my histogram. I'm going to do zoom 9 once I turn on the stat plot. And if I look at that right there, I don't see strong skew, which is good because I have a small sample size. It's less than 30. So I actually need to look at the shape of the sample. So now what I'm going to do is skew shows, histograms show me skew. So I'm going to do second y equals, go back to stat plot. But what I'm going to do now is I'm going to turn on box plot with outliers, because this actually does a really good job of showing you outliers. So in this case, there are no outliers. So what I would do is I'd copy this box plot down. I know it says dot plot here, but I'm just going to be honest with you. If you're putting the data in the calculator, I would go ahead and I would put down the box plot. So what I'm going to do is this. Okay, so now here's the deal. Never leave it just kind of floating. What I'm going to do is hit trace. I know that this thing goes from 0. Was it 0.9? Is that right? Hang on, something's off. Oh, I know what I did wrong. I actually did it on L1. That's my mistake. Good, I'm just glad I showed you that. I made a mistake. So second y equals. I don't want to run it on L1. I actually want to run it on L3. I'm glad I did that because I can actually show you the mistake. So we're going to go ahead and zoom 9. And if we look at that difference, I will be honest with you, that's not really strong skew. That's almost a uniform distribution, to be honest with you. That's almost a uniform distribution. I know it kind of has that shape to it, but I'm going to go ahead and say that's not strong skew. What I'm going to now do is I'm going to go back and look at the history, the dot plot, box plot with outliers. Zoom 9. And that's really what I'm going to put down. So what I want to put down for real is this, big box. And what I want to do is I want to put the scale on it. So I know it runs from 0.9 to 4.9. So what I do, if I hit trace, it goes from 0.9 to 4.9. So what I'm actually going to do is I am going to mark my number line 0, 1, 2, 3, 4, 5. So that's how I'm going to label. I'm going to label this right here, and this is actually the difference, A minus P. And I'm going to say there's no strong skew. There's no outliers. Okay, now it says find the mean and standard deviation. So what I'm going to do is I'm going to do stat. I'm going to do calc. I'm going to do 1-bar stats, but I'm going to run it on column 3. And what I'm going to find out here is that the mean is 3.02. X bar diff is 3.02. The standard deviation of the difference is equal to 1.316. So now what I have here is if I wanted to interpret those basically in the amount of time a teenager spent online was 3.02 hours longer than parents believed or perceived on average. Okay. So now, let's do our interval. So since this is, even though it's 2 samples, we're running it on that 1 sample. So we're going to do it just like we did in 1 sample interval, P. What we're going to do when we declare that is you can declare each one of these, but honestly, all I care about is this, mean difference. So what this is the true mean difference in time spent online. And what I'm going to say is actual minus perceived. That's what I'm going to be trying to figure out. So I'm going to run it on this. I don't need to declare each one of those individual samples. So A, going to validate my assumptions. First one is random. So in this case, we're going to look at, does it say random in here? And we know that it said random sample up top, random sample. So it states random. Now we're going to do independent. And this is a one sample again. So when we do independent, we want to do the 10N check. So we're going to do 10N, which is 10 times 12, which is 120. We're going to compare that to the overall population. In this case, we want to take a look and say, does it seem reasonable that there are more than 120 teenagers? Safe to assume more than 120 teens. And now we're going to do our large enough, and that's where we're going to steal that picture from up top. So what we want to do is, from part A, we see no strong skew. And no outliers. Now, what would happen is if we hadn't done part A, you would have needed to draw that picture down here. So now what are we going to do here? We're going to construct a one sample T interval for true mean difference at 90% confidence. And again, this is a good place to try and go figure out what the T star is. T star is based on degrees of freedom. Degrees of freedom are n minus 1, so that's 12 minus 1, that's 11. So what I'm going to do is I'm going to go to table B. I'm going to go to the 11 row. And what I need to do is I need to go to the 90% column. So it's this column right here. When I go to the 11 row, it's 1.796. Make sure I get it right. Nope, it is 1.796. So our degrees of freedom here are, I'm sorry, we had 10 teens. Why am I doing it that way? We had 10 teens. Let's take 10. So 100, 100, 10. So that tells me that's going to be degrees of freedom 9. All right. So we go to 9, we go to 90%, and we find out that that number is 1.833. So that tells me my T star is 1.833. And now for my interval, it's just like a one sample. We're going to use X bar plus or minus T star times SX over the square root of N. Well, in this case, we already figured out X bar was 3.02. So this is 3.02 plus or minus. We just figured out T star is 1.833. We figured out that standard deviation is 1.316 over the square root of 10. And now we're going to go to our calculator to get that. And the way you do it in the calculator is stat, tests. And what we're going to do is a one sample T interval, which is number 8. We can either do it on the data or we can do it on the stats. Since it's already in the calculator, I'm going to go ahead and do it on L3 at 90% confidence. And eventually it's going to pop up and it's going to tell me that the interval here is 2.2574, comma 3.7826. So there's my interval. And I'm going to conclude it with the C. We are 90% confident the interval from 2.2574 hours to 3.7826 hours captures the true mean difference in time spent online, actual minus perceived. And there's my interpretation. Now here's the deal. The follow-up question is often going to be, is this evidence that parents are unaware of how much time their kids are spending online? And the answer to that would be yes, because this is all positive. They always, in this case, there was always a positive difference between the actual and the perception. So that means that based on this interval, it's pretty safe to assume that parents don't realize how much time their kids are spending online. So the big takeaway from this is called a matched pair. Okay, so what I mean again by match pair is the following. We have two samples, but they can be paired in some way. Now, the easy way to see this is oftentimes it's going to be a before and after situation. We're going to be doing some sort of, an exercise program or a meditation program. And we're going to measure my blood pressure before I start the meditation and my blood pressure after I take the meditation. And since I'm receiving both treatments on that, it's a matched pair. What that allows me to do is to see if there is actual difference. Now, that is the easier one. I will let you know from time to time, there are going to be ones that aren't as straightforward. It isn't the same person, like this one. We are comparing the amount of times teens actually spend online to their parents' perception, but it's always done on just that one teen. A very common one that they like to do is on twins. So what they'll do is they'll run an experiment where identical twins will each receive one of two different treatments, and then they'll compare it because genetically identical twins are supposed to be as similar as you can get. There's a pair. I've seen match pair where they talk about a married couple and they do one treatment to one spouse and one treatment to the other spouse. And then they compare. And the belief is that there is a lack of independence between that because a married couple already kind of has something in common. So the big thing to look for is that singular mean versus the plural mean. Mean, difference, you treat as a one sample. Difference in means, plural, you treat as a two sample. So hopefully that helps.